For more than 50 years, physicists have predicted that a particle like this should exist. Not a particle made from quarks like protons and neutrons, not an atom held together by electromagnetic attraction, instead something much stranger, a particle made primarily from the carriers of the strong nuclear force itself. Physicists call it a glueball. Now, researchers working with the BESIII particle detector in China say a mysterious particle known as X2370 fits the expected properties of the lightest pseudoscalar glueball better than competing explanations. After combining years of measurements from a dataset containing 10 billion BESIII particles, the team argues that a glueball must be the dominant component of X237C8 EVER2. If that interpretation survives further scrutiny, physicists may finally have strong evidence for one of quantum chromodynamics' strangest predictions. The force that normally binds matter together can also bind itself into matter. To understand why that is so unusual, start inside a proton. A proton is not a simple solid ball. It contains quarks interacting through the strong nuclear force. That force is carried by particles called gluons. The name is appropriate. Gluons effectively provide the glue that confines quarks inside protons, neutrons, and other hadrons. But gluons differ fundamentally from photons, the particles that carry electromagnetism. Photons do not carry electric charge, so ordinary light does not directly attract more light through electromagnetism. Gluons are different. They carry what physicists call color charge, the type of charge associated with the strong interaction. Because gluons themselves carry this charge, they can interact directly with other gluons. That creates a remarkable possibility. If gluons can attract and interact with one another, then under the right conditions they should be able to form bound states without requiring ordinary valence quarks. Those hypothetical objects are glueballs. Quantum chromodynamics, or QCD, has predicted them for decades. Computer calculations known as lattice QCD have even estimated the masses and quantum properties that the lightest glueballs should possess. For the lightest pseudoscalar glueball, calculations generally place the mass somewhere around 2.3 to 3.0 billion electron volts divided by the speed of light squared. That is exactly where X2370 appears. The particle gets its name from its mass, which is close to 2.4 gigaelectron volts. BESIII first observed X2370 in 2011 during decays of another particle called the BESIII. Later measurements confirmed it in additional decay channels. In 2024, researchers determined that X2370 has quantum numbers written as 0- or 0-, the same quantum numbers expected for the lightest pseudoscalar glueball. That was intriguing. But matching the predicted mass and quantum numbers was not enough. The problem is that particle physics contains many possible composite states. A resonance appearing near the expected glueball mass could still be built from quarks, contain 4 quarks, resemble a molecular state made from other hadrons, or be a mixture of several configurations. This is why glueballs have been so difficult to identify. The strong interaction does not create perfectly isolated categories. A pure gluonic configuration can mix with ordinary quark-based particles if they share the same quantum properties. Finding a particle at the right mass is therefore only the beginning. Physicists need to examine how it is produced and, crucially, how it decays. That is where the newest BESIII analysis becomes especially interesting. The team studied 10 billion BESIII events. The BESIII particle contains a charm quark and an anti-charm quark. One way it can decay is by emitting a photon while producing a gluon-rich environment. That makes radiative BESIII decays particularly attractive places to search for glueballs. If a particle is dominated by gluons, researchers expect it to be produced relatively strongly in exactly these conditions. X2370 satisfies that expectation. Then researchers examined what X2370 does after it forms. In the new study, they searched for a particular decay involving a K-star meson and a neutral kaon. They did not find significant evidence for it. Normally, a particle with particular quark content might be expected to decay into channels that reflect those quark flavors. The suppression of this K-star kaon channel instead supports the idea that X2370 behaves like a flavor singlet state, meaning it does not strongly favor one ordinary light quark flavor structure over another. According to the BESIII collaboration, X2370 is the first flavor singlet light hadron observed above 1 gigaelectron-volt. That adds another piece to the puzzle. Its mass fits, its spin and parity fit. Its production in gluon-rich J-ply decays fits. Its decay patterns increasingly fit, and alternatives based primarily on ordinary quark configurations become harder to make consistent with all of those observations at once. This is why the researchers do not merely call X2370 glueball-like. Their new analysis argues that a dominant glueball component is essential for naturally explaining the complete set of measured properties. But there is an important word in that sentence: component. Physicists are not necessarily claiming that X2370 is a perfectly pure ball containing nothing except gluons. Real QCD states can mix. Think of two musical notes played simultaneously. If their frequencies and interactions allow them to influence one another, the sound you measure may contain contributions from both. Particle states can behave similarly. A physical resonance may contain a dominant gluonic component while still mixing with quark-antiquark configurations. Some theoretical work has specifically investigated whether X2370 could mix with other pseudoscalar states rather than existing as an absolutely pure glueball. That nuance matters because headlines saying scientists discovered a particle made only from force are stronger than the evidence currently supports. Nature described the result as strong evidence for the mysterious glueball, while science reported it as an elusive new form of matter whose identification has taken decades. The BESIII collaboration itself concludes that the lightest pseudoscalar glueball is the dominant constituent of X2370. So why would confirming a glueball matter? Because it tests one of the most unusual features of the strong force. In electromagnetism, the force carrier does not normally bind itself into massive particles, but QCD is non-abelian, which means its force carriers interact with one another. Glueballs are one of the clearest physical consequences of that difference. Observing one would show that gluons do not merely transmit the strong interaction between quarks. Their own interactions can create a massive composite object. There is an even stranger consequence. Individual gluons are considered massless. Yet a glueball can have substantial mass. How? Most of the mass does not need to come from the rest masses of its ingredients. The energy stored in the strong interaction itself contributes to the mass of the bound system through Einstein's relationship between mass and energy. This is not unique to glueballs. Much of the mass of protons and neutrons also arises from QCD dynamics rather than simply adding the tiny masses of their constituent quarks. A glueball would make that phenomenon unusually pure, a massive object created predominantly from the dynamics of massless force carriers interacting with one another. That makes X2370 more than another entry in a particle table. It could become a laboratory for understanding how the strong interaction creates mass, and the search is not over. Physicists will want independent measurements and more precise studies of additional X2370 decay channels. Other experiments can search for the same state under different conditions. Researchers will also compare its measured properties with increasingly accurate lattice QCD calculations. The question is not simply whether X2370 contains gluons. Every hadron contains gluonic fields. The question is whether its identity is dominated by a bound gluonic state in the way QCD predicted decades ago. That is a much harder standard. But for the first time, multiple independent clues are converging on the same answer. More than a decade ago, X237c appeared as one unexplained resonance among many. Then its mass became interesting. Its quantum numbers matched. Its production pattern matched. Now another expected decay signature has failed to appear, strengthening the case that the particle does not behave like an ordinary quark-built hadron. Piece by piece, the alternatives are narrowing. For decades, physicists have known that gluons hold ordinary matter together. The stranger prediction was that, under the right conditions, the glue should not need anything else. It could bind to itself. And somewhere inside 10 billion particle decays recorded in China, researchers may finally have found the object that proves it.